Bismillah ar-Rahman ar-Rahim. This is lecture 5, and it's chapter 6 on eigenvalues and eigenvectors. In order to understand what is meant by eigenvalues and eigenvectors, we begin by considering the action of a matrix on a vector. Almost all vectors change direction when multiplied by a matrix. So the action of A onto X changes it to B. Certain exceptional vectors x are in the same direction as A times x. Those special vectors are called eigenvectors. So Ax becomes lambda x. Lambda is a number which we call the eigenvalue of A. The word eigenvalue is derived from the German root eigen, which means characteristic. So eigenvalue is a characteristic value of the matrix. Lambda tells us whether the special vector x is stretched, made longer, or shrunk, shortened, or reversed, or left unchanged when multiplied by A. We may find lambda equals 2, or 1/2, or -1, or 1. The eigenvalue lambda could also be 0. The equation Ax equals 0x means that x is in the null space of A. If A equals the identity matrix I, then every x or all vectors are eigenvectors of I with lambda equals 1. Most 2x2 matrices have two eigenvector directions and two eigenvalues. How do we calculate eigenvalues and eigenvectors? Ax equals lambda x can be written as A minus lambda I times x is equal to 0. So the determinant of A minus lambda I must be 0. So we take an example of a matrix A whose columns add to 1. See, the components of each column add to 1. 0.8 plus 0.2 is 1. 0.3 plus 0.7 is 1. So we would like to find the eigenvalue and the eigenvectors. Okay. So if we take the determinant of the shifted matrix A minus lambda I, okay, then expanding the determinant, 0.8 minus lambda times 0.7 minus lambda minus 0.3 times 0.2, which is 0.06. And if we expand the brackets, we come up with lambda squared minus 1.5 lambda plus 0.5 equals 0, which factors into lambda minus 1/2 times lambda minus 1. So we have two roots, or two eigenvalues, lambda 1 equals 1 and lambda 2 equals 1/2. Now the matrix A is a special matrix in which the components of every column add to 1 and are all positive. It is called a Markov matrix, and it is important in applications in economics. It multiplies a vector U0, an initial vector, whose components also add to 1, x and 1 minus x. And this process, of this matrix, is usually applied several times to this vector. So we need to calculate A times U0, A square U0, A cube, and so on up to AN, and n could be very large. We can calculate A square and A cube, but it's not easy to calculate up to A to the power 100. So we will see how to calculate A raised to any power n by using eigenvalues and eigenvectors. Okay. So we need to calculate the eigenvectors now for this matrix. For lambda equals 1, we solve A minus I, x1 equals 0. Now, using the initial vector U0, x1 minus x, this becomes minus 0.2 and 0.2 in the first column, 0.3 minus 0.3 in the second column, and we subtract lambda 1 equals 1 along the diagonal. So using Gaussian elimination, we get a row of zeros because row 2 is the same as minus row 1. Just adding, we get 0 and 0. Okay. Now, x 1 minus x is a free variable, and if we substitute by solving from the first row, minus 0.2 times x11 plus 0.3 x12 equals 0. Okay, and x12 is the free variable, which is 1 minus x here. So if we substitute here for x and 1 minus x, we find that x is equal to 0.6. Hence, the first eigenvector is 0.6 and 1 minus 0.6, which is 0.4. So this is the first eigenvector of the Markov matrix. You can check that this is really an eigenvector, that it satisfies the equation ax equals lambda on x. Okay, so we multiply a by this vector, 0.6, 0.4, we find that the result is the same vector, which is the eigenvector multiplied by the eigenvalue lambda equals 1. If we repeat the process, a squared times x1, we get lambda 1 squared times x1. And so a to the power 99 times x1 is just lambda 1 to the power 99, which is 1 to the power 99, which is 1 times x1. So the result is x1. Okay. The second eigenvector for lambda 2 equals 1/2. Okay, we substitute into the shifted equation, a minus 1/2 I times x2 equals 0. Okay, and again, using Gaussian elimination, we find a row of zeros, so we have x22 is a free variable. Okay, and we set it equal to 1 or minus 1. Okay, and we find that x2 is equal to 1 minus 1. Okay, now ax2 is 1/2 times x2, okay, which is 0.5 minus 0.5. If we multiply by a again, so a squared times x2 becomes 1/2 squared times 1 minus 1, okay, and if we calculate a to the power 99, it becomes 1/2 power 99 times 1 minus 1, which is a very, very small number here, okay, and we get a very small vector, a negligible vector, almost equal to 0. Now we know that a x1 equals lambda 1 x1 is a linear combination of the columns of A. Lambda 1 x1 is a linear combination of the columns of A. So the vector x1, which is 0.6, 0.4, is really 0.6 times the first column of A plus 0.4 times the second column of A. Okay. You can do this by substituting this equation and using Cramer's rule, find the values of the coefficients, which are 0.6 and 0.4. Okay, so this is the first eigenvector written as a linear combination of the columns of A. Also, ax2 equals lambda 2x2 is a linear combination of the columns of A. So 1/2 times 1 minus 1 is really 0.8, 0.2, the first column minus the second column. It's 0.5 minus 0.5. So the columns of A are a basis of R2. Note that x1 and x2 are linearly independent. Linearly independent means that if we put these vectors x1 and x2 as columns of a matrix, then we'll find that this matrix is invertible. That is, the determinant of this matrix is not equal to 0. So x1 and x2 can be chosen as bases for R2. And we can express any vector as a linear combination of x1 and x2. Okay. And here's a check that this matrix has a determinant equal to -1, which is not 0. So x1 and x2 are a basis of R2, okay, so that any vector in R2 can be expressed as a linear combination of the eigenvectors. So if we take the columns of A, the first column can be expressed as a linear combination of x1 and x2, as we see here. Okay. Suppose we multiply this vector by A, then each eigenvector is multiplied by its eigenvalue. For the first column of A, we get A times the first column equal to the first column of the first eigenvector, 0.6 and 0.4, plus 1/2 times 0.2 minus 0.2, which is 0.1 minus 0.1. If we multiply by A 99 times, so we get A to the power 100. The first eigenvector remains the same because lambda 1 to the power, which is 1, to the power 99 is 1. But the second eigenvector, okay, is multiplied by the second eigenvalue, 1 to the power 99, which is a very small vector. So this is negligible compared to the first eigenvector. So this will be the first column of A to the power 100. To get the second column of A to the power 100, we take the second eigenvector, the second column of A, and express it using the eigenvectors as a basis. We will find that it is 1 times the first eigenvector minus 0.3 times the second eigenvector. Multiplying by A now, the first eigenvector remains the same, the second eigenvector is multiplied by 1/2, and if we go up to, if we multiply by A to the power 99, we get A to the 100 equal to the first column 0.6, 0.4, plus 1/2 to the power 99 times 0.3, 0.3, which is a very small vector. So the second column again equals 0.6, 0.4. So A to the power 100 has become this matrix whose columns are equal. And in the language of systems, this is called a steady state. That is, the process that has been repeated 100 times has reached a steady state. Okay, this is a Markov process. Okay, if we look at the action of the matrix A on the eigenvectors, we see AX1 gives x1 whose length doesn't change. Okay, and A times x2 gives us 1/2 of x2. So it is shortened. And if we multiply a second time, the first column remains, this first eigenvector remains the same, while the second eigenvector is reduced by 1/2 again.